before I begin? Any questions? Yes.
So I started my 3D printing, but I was also looking at one of the options there for the purchasing of the metal
Yeah.
one, and it seemed to me, at least when I first looked at it, that there was one more joint on that one than there was on the 3D printed one. Is that correct?
Yes. Sneaky. As you know, there is no free lunch. So which means if you buy the, I'm glad you caught it. So if you buy a ready-made robot arm, you will have to modify the code so that that robot arm can work with the app and the Arduino code that you have. So basically you will have to add one more servo joint and control it. It's not difficult, but it does involve some work. That's why I said, even if you buy the 3D printed, whether you buy off-the-shelf arm or if you construct 3D printed arm, you will still get the same points. Because if you want to get that off-the-shelf metallic arm working, you will have to add one more joint, which means you will have to modify the Arduino code. Again, it's cut, copy, and paste, and the app so that the robot arm functions properly. Smart. Okay. So what I'm going to do is I'm going to start today's lesson. And in today's lesson, I'm going to look at some problems where the rules are not satisfied. So before I start the problem, let me write down the rules. Rule number 1, Zn axis is the actuation axis. The second rule is Xn must be perpendicular Zn and Zn minus 1. Then Xn must intersect Zn and Zn minus 1. And last is we have to use RH coordinate system. Now we have looked at the problems when you satisfy all the rules. But now let me take some examples where the rules are not satisfied. And please understand the problem that I'm solving, they are directly related to the problems in assignment 2. So please pay attention. So this is the first revolute joint. Then you have one more revolute joint. Then this revolute joint is attached to a prismatic joint. And this prismatic joint has the actuation direction as shown over here. So this is my revolute joint. Then this revolute joint is attached to the second revolute joint. This second revolute joint is attached to prismatic joint. Now, what I want to do is, I want to first and foremost set up the coordinate system. So this is going to be my Z0. This is going to be my Z1. And clearly, this is going to be my Z2. And I need to set up the coordinate system. And this is going to be my end effector. We will worry about the end effector coordinate system at the end. But first, please try to understand all my Z axis are passing to the direction of actuation. So Z0 can go up, can go down, doesn't matter. Z1 can come out, go in, does not matter. Z2 can go towards right or towards left, does not matter. But this is how I have chosen it. Then I'm gonna choose this as x0. Please note there is no other Z before Z0, so it doesn't matter. But once I have X, once I have Z, this becomes my Y. So I have Y0, something like this. Now I need to specify X1. The condition for X1 is it must intersect Z1 and Z0. It must be perpendicular to Z0 and Z1. So most logical way of drawing that is this. I mean, there is no harm in drawing in the opposite direction, but I just chose this direction. But please note, X1 cannot be going up or down. If X1 goes up or X1 goes down, it's not perpendicular to Z0. Do you agree with me? I cannot draw under no conditions. Actually, and let me draw this. Under no conditions, I can draw X1 like this. Because if I were to draw X1 like this, X1, even though it's perpendicular to Z1, X1, even though it is intersecting with Z1, X1 is parallel to Z0. So it violates the rule. Everyone understood this? So this is the right way to draw X1. X1, Z, I got Y. So this is my Y1. Now, next I need to find out what is my X2. X2 has to intersect Z1, X2 has to intersect Z2, and X2 has to be perpendicular to Z2 and Z1. Now, I want you for a moment to think about the possible options. And this is very, very important. So I want you to see, I can have X1 like this, or I can have X1 in this direction. X1 has to be perpendicular to Z2. I mean, X2 has to be perpendicular to Z2. So possibly I can have X2 here, or I can have possibly X2 here. Do you agree with me? Now here is the question. No matter what I choose, my X2 is not going to be intersecting with Z1. This is very, very important. And I'm going to write this down here. Note, side note. X2 does not intersect Z1. Do you agree with me? Yes. Yeah, X2 has to be perpendicular to Z2 and X2 has to be perpendicular to Z1 too.
So then there will be only one option, the upright.
Even though if you have upright one, X2 is not intersecting with Z1. Because if you see, your Z1 is here, your X2 is here. So they are parallel. They are not intersecting. So, but you're right. So now I will repeat this once again because this is very important. Clearly, you don't have any control over Z2. Z2 is fixed. Do you agree with me? Because Z2 has to pass through the joint coordination or joint actuation. So X2 has to be perpendicular to Z2. So there are only two possibilities. X2 can be here or X2 can be here. Do you agree with me? Out of these, let me see. If I were to choose, and this is very important, if I were to choose X2 for a minute, please pay attention here. For a minute, if I were to choose X2 here, and I'm going to say this is going to be my X2. Please understand that I'm breaking two rules. Do you agree with me? X2 is not perpendicular and X2 is not intersecting. Do you agree with me? However, if I do this, then if I choose this as X2, then you will realize that x2, even though it's not intersecting, but it is perpendicular. Do you agree with me? So in this condition, and I will write this down here, which is very important, x2 not intersecting, but perpendicular to z2 and z1. You agree with me? So this is the case where out of 4, only one rule is broken. So we can live with this. And then I will finish the triad. This is going to be my triad. This is y2. And again, my end effector, I'm going to duplicate the same triad. But then I'm going to check if I were to use this as z3, if I choose this as x3, if I choose this as y3, I want you to understand z3 doesn't really matter because there is no joint. I just assume z3 to be parallel and in line with z2 for convenience. But when I chose x3, it is very important. When I chose x3, I made sure that x3 is perpendicular to z3 and x3 is perpendicular to z2. Everyone understood this? I will give you a minute to think about it. Now I want you to understand, this is my frame 0, this is my frame 1, this is my frame 2, and this is my frame 3. Out of that, frame 2 does not satisfy all the criteria. So frame 2 has some issues, and we will look at that in just a second. Everyone understood this? Any questions on x? When do you say x2? Do you mean x of? No. Ahmad, I don't understand your question, but when I say x2, I'm going to highlight this. This is the vector that I'm looking at. So now what I'm going to do is, I'm going to start with the very basic. So first and foremost, 0 or 1. And by now you should know this. Oh, let me say this is theta 1. This is theta 2. And since this is a prismatic joint, I'm going to call this distance as d3. And please note this d3 changes with respect to time, just like the joint axis where the joint rotate, this prismatic cylinder goes forward and backward. So cosine theta minus sine theta, cosine theta, 0, 0, 0, 0, 1. Let's not forget the projection matrix. And the projection matrix is going to be x1, y1, z1, x0, y0, z0. Look at x1 is in the same direction as x0. Y1 is in the same direction as z0. And z1 is in the same direction as minus y0. Are you with me so far? Yeah. Once you multiply these two, you have the actual rotation matrix. First row, first column, 0, sine theta 1, sine theta 1, 0, minus cosine theta 1. First row, first column, 0, first row, second column, last row, third column, 0.
Excuse me, I think someone's in the waiting room.
You want me to go slowly through this, Matt? Oh, okay. So first row, first column. So cosine theta 1, multiplied by 1 minus sine theta 1 multiplied by 0 and 0 multiplied by 0. That gives you cosine theta 1. Then second row, first column, third row, first column. That gives you the first column. So this is just the matrix multiplication that we are doing line by line. Do you want me to write it down? So now the question is, what is 1 R2? 1 R2 is again cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. Then you have the projection matrix, which is x2, y2, z2, x1, y1, z1. Now x2 is aligned with x2 is aligned with y1. x2 is aligned with y1. Then z2 is aligned with x1. So here there is 0, 0, and y2 is aligned with z1. Everyone understood this? Now at this point, what we want to do is we want to construct the homogeneous transformation matrices for 0R1 and 1R2. So what I'm going to do is I'm going to give you some distances. Actually, and this is super important. So what I want to do is I'm going to say this distance is A1. This distance is A2. So let me write down the homogeneous transformation matrices. Actually, it might be just a good idea to, because this is going to be super important. So let me just write this down. So 0 H1. If you look at 0 H1, this is going to become cosine theta 1, 0 sine theta 1, 0 sine theta 1, 0 minus cosine theta 1, 0, 0, 1, 0. And let me, before I write this down, let me just, so let me know if this is a little bit fast for you, okay? So right now, what I have is I need to fill in 3 blanks.
So that's the distance that we're looking for.
That is the distance between, and I will write this again, frame 1 and frame 0 along x0, y0, z0. So I need to go back a step, and please note, this is my frame 0, this is my frame 1. So these 2 frames are aligned in the x0 direction. These 2 frames are aligned in y0 direction, but these 2 frames are apart by distance a1 along z0 direction. You agree with me?
Yeah.
Okay. So I can write this down as 0, 0, a1. Everyone understood this? Now comes the tricky part. Now what I need to do is I need to write down the homogeneous transformation matrix for 1R2. And I'm going to say this once again. R2 is where the frame violates. So frame does not follow rules. So how do we circumvent this problem? Now, direction of theta, yes, direction of theta is, I'm assuming theta is positive. So if you curl your fingers in the direction of theta, your thumb is pointing towards positive z-axis. Now, whenever there is a violation of rule, what we do is we translate the frame. Once again, I repeat, whenever there is violation of rule, we translate the frame. And what do I mean by frame translation? For a minute, think about the frame number 2. For some reason, if I translate this frame by distance A2 towards the left-hand side, if I translate the frame 2 towards the left-hand side to the point that it intersects with frame 1, do you agree with me? All the rules are satisfied. I'll repeat this once again. So what I want you to do is, I want you to think about for a second, it may be a little difficult to visualize the very first problem. So assume that I take that frame from there and translate it here.
You're saying putting frame 2 literally on top of frame 1.
Yeah, that's what I am asking you to do.
But if you do that, then the A2 distance that we have, that you basically are telling me
Hold on,
that goes to 0.
No, hold on. Just a second. One baby step at a time. So now what I'm gonna do is I'm gonna translate the frame 2 on top of frame number 1. As soon as I do this translation, do you agree with me? As soon as I do this translation, do you agree with me? All the 4 rules are satisfied.
Yeah.
Any questions here? I will give you a minute to think about it. Can you see my x2 is now perpendicular to z2? X2 is perpendicular to z1. X2 is intersecting z1. X2 is intersecting z2. Do you agree with me?
Yes.
So what I did here is I translated the frame 2 to 1. Now the key question is, what happens because of this translation? So as clearly pointed out by our friend, as soon as I translate the frame, that A2 distance has vanished. In other words, frame 1 and frame 2, they are no longer A2 distance apart. Frame 1 and frame 2, they are no longer A2 distance apart. The distance between these 2 frames is 0. Do you agree with me? So what does that mean? That means, and this is very important, that's why I want to show it to you here separately, and I will repeat this. Now I want to write 1H2. Please note, in 1H2, frame 2 is coinciding with frame 1. So what I'm going to do is, I'm going to take the rotation matrix. The rotation matrix is going to be this guy. Rotation matrix is going to be this guy. And let me work this out real quick. Check this out. First row, first column, cosine theta 1. So this becomes minus sine theta 2. First row, second column, this becomes 0. First row, third column, cosine theta 2. Second row, first column, cosine theta 2. Second row, second column. Second row, third column. Third row, first column. Third row, second column. Third row, third column. So I got this rotation matrix. So for homogeneous transformation construction, I would take this rotation matrix and place it here. Zero, 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 1. And that rotation matrix is sine theta 2, 0, cosine theta 2, cosine theta 2, 0, sine theta 2, 0, 1, 0. Now, the next question is, no, did I miss a negative sign here? This is negative, right? The first. So now the key question is, what happens here, here, and here? Now, please note, these two frames coincide with each other. What it means is I'm going to write 0, 0, 0. You agree with me? I will give you a minute again to think about it. What I did, I translated the frame 2 so that it coincided with frame 1. And the reason I did that, because I wanted my rules to be satisfied. But then the question comes, and this is very important, and there are slight varieties of how to handle these exceptions, but I'll give you a very simple trick. Now, for a moment, I want you to look at frame 3 and the translated frame 2. So I want you to look at frame 3 and the translated frame 2. Are you with me so far? Frame 3 and translated frame 2. Do these two frames satisfy the 4 rules? So I will repeat it once again. What I want you to do is, I want you to look at this frame and this frame. And I want you to tell me if these two frames satisfy the 4 rules. So the answer to question is yes. So what that means is I can directly go solving the problem. So what I'm going to do is, I'm going to actually, there are different ways of working out this problem, but I'll give you a simple trick. Please note, if you look at the frame joint, which is the prismatic joint does not have any rotation. Prismatic joint does not have any rotation, which means its rotation matrix is going to be an identity matrix. Its rotation matrix is going to be an identity matrix. So what I can do is, I can write this something as simple as 2R3. Now this 2 is translated frame, okay? This rotation matrix is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. Believe it or not, we cannot forget the projection matrix. The projection matrix is x3, y3, c3, x2, y2, z2. And please note, x3 is aligned with translated x2, y3 is aligned with translated y2, and z3 is aligned with translated z2. Do you agree with me? Yeah. I'm going to rewrite it over here. x3, y3, z3 are aligned with translated x2, y2, z2. So do you agree with me? This is going to be 0. This again is going to be an identity matrix. So which means this rotation matrix is nothing but an identity matrix. Now the question comes is what happens now for the homogeneous transformation? And this is the first. Now the homogeneous transformation now has to deal with translated frame 2 and the final frame 3. Okay, so the homogeneous transformation, and I'm going to rewrite it over here. So it's going to be 2H3, but please note this is translated. And this is actually unmoved or end effector frame. So I'm going to go ahead and I'm going to say 1 0 0 0 1 0 0 0 1 0 0 0 1. But the key question is, what do I do here? Let's stick to basic. What I have here is the distance or position distance between frame 3 and translated frame 2 along x2, y2, z2, and that has to be valid. This is super important. That has to be valid for all the values of theta 2. The distance between the end effector frame, which is frame number 3, and the frame 2, which now coincides with frame 1. Why did we coincide that with frame 1? Because the rules were not getting satisfied. So please note here is the distance between frame 3 and translated frame 2 can now be written as something like, check this out, you are going to have x2. So this is going to become, just a second, between the translated frame 2, which is on the very end left side, and the end effector frame. Can you see the distance between these two is A2 plus D3?
Yes.
Do you agree with me?
Yes.
Okay. That A2 plus D3 is sort of the lever arm, and I want it to be valid. I want it to be valid for all the values of the joint rotation. I want that to be valid for all the joint rotation. So this is theta 2, by the way. It may look like 1, but this is theta 2. This is theta 2. So as that lever arm rotates, it is going to have a cosine component horizontally, and I will repeat that once again. It will have a cosine component horizontally, but what is my horizontal vector? Z2. Are you with me so far? So look at Z2. Once that arm rotates, A2 plus D3 cosine of theta 2 will be along Z2, and A2 plus D3 addition multiplied by cosine of theta 2 or sine of theta 2 will be around x2. So this is going to become, and so this is going to become, actually let me rewrite this over here. So this is going to become A2 plus D3 sine of theta 2. This will be 0, A2 plus D3 cosine of theta 2, and there will be 1 here. So this is super duper important. And I will give you a minute to think about it.
So are we accounting for that distance that we basically said we're gonna set this equal to 0 in order to fulfill the rules? By doing that, we're fulfilling that sacrifice that we made earlier.
Right. So now the conditions are satisfied. And the conditions are satisfied for all the frames as long as we translated the frame. But then the distance between frame 2 and frame 3 is no longer D3. It is A2 plus D3. And if you take the cosine and sine components, the horizontal vector, remember, it always has to be in the previous coordinate frame. So we are trying to relate frame number 3 with frame number 2. So the vectors should be Z3, X2, and Y2. Can you see Y2 and Y3? They are in the same plane. So the only difference you are going to have, the difference between the orientations, they are going to have the projection along X2 and the projection along Z2. That's why you have those terms over here. Everyone understood this? So this would be the perfect. There is no rotation on the prismatic joint. Prismatic joint is purely translational. That's why we have just identity as the rotation matrix. Prismatic joint is going to add variation in the position. Now, at this point, what we should do is we should go on to the MATLAB and then work this problem inside MATLAB. Yes.
We don't do the translation thing, and we solve it, and we will get the A2 cos theta, A2 sin theta, second frame reference. Because in the end, we'll have to multiply these homogeneous matrices together anyway. So won't that take care of this?
No. I tell you what will happen. Can I solve this problem and tell you what will happen if you were to do the other way? Basically, what is happening here is, and you'll appreciate it in just a second. If you were to follow the approach that we just talked about, if we don't translate the frame, what will happen is you would have A2 cosine theta 2, A2 sine theta 2, but you will not have D2 cosine theta 2 and D2 sine theta 2. You see what I'm saying?
But I understand that. But then when we
Multiply, then again you will not. The results will be different. And what I'm going to do this time, I'm going to go to MATLAB. Any questions from my online students? Why do you take and took out all rotation angles on your last frame? Won't there be rotations? So prismatic joints, no rotations, only rotary joints will have rotation. So I'm gonna share my MATLAB screen. And I will go ahead and program this. So SYMS, theta 1, theta 2. Then I'm gonna have A1, A2, and then I will have D3. Then I'm just gonna go ahead directly and write the homogeneous transformation matrices. H01 is equal to cosine theta 1 0 sine theta 1 0 sine theta 1 0 minus cosine theta 1, 0, and so on, and so on. 0, 0, actually this is 1, 1, 0, and then I'm gonna have A1, and so on. 0, 0, 0, 1. Then I will have H12. H12 is minus sine theta 2, 0, cosine theta 2, 0, cosine theta 2, 0, sine theta 2, 0, 0, 1, 0, 0, 0, 0, 0, 1, and last H23 is going to be 1, 0, 0, A2 plus B3 sine theta 2, and so on. 0, 1, 0, 1, 0, 0, 0, 0, 1. I'll try to be a little bit more systematic. Here is going to become A2 plus D3 multiplied by sine, cosine theta 2. The last 0, 0, 0, 1. So these are the homogeneous transformation matrices. Let's make sure that I haven't made any mistake. Then I will have H03 is equal to H01, H12, H23, and you can actually add, simplify, and run the script. And now you are gonna get a nice expression over here. And then you would have, so that is gonna give you, so just look at the homogeneous transformation matrices. Let me make sure that I got them correct. Minus sine theta 2, 0, cosine theta 2, cosine theta 2, sine theta 2, 0, 1, 0, 0, 1. So basically Once you add that, you are gonna get this expression, and that expression is gonna tell you the sine and cosine components, what they are gonna look like for your final system. So that is how you would solve a forward kinematics problem wherein you have different conditions. Okay, now let me take one more problem real quick. So I'm gonna let me take another problem. This is again similar to the problem in the assignment 2. So you have a revolute joint, then you have the prismatic joint, and then you have another prismatic joint. So you have a revolute joint, then you have a prismatic joint, and you have a prismatic joint. And what we need to do is we need to work out the forward kinematics. So the first step is always assign the coordinate frames. Z0, this is Z1, C2, then you are going to have X0, then you are going to have Y0, then here there is going to be X1, there is going to be Y1, and this is going to be, since this is Z, what I'm going to assume is my X2. I'm going to assume something like this, and I'm going to assume my Y2 is something like this. And I will give you a minute to check if these three frames are satisfying my 4 rules. This is going to be Y2, sorry, Y3. I'm going to say this is Z3, going to be X3. And I'm going to give you some distances. This distance is A1. This distance is D2. And this distance is D3. One thing to note, when you solve the robotics problem, typically A's are constant. So for example, the distance between the prismatic joint and the revolute joint. So this is your frame 0. This is your frame 1. This is your frame 2. This is your frame 3. So distance between the 0th frame and the first frame, which is the prismatic joint. Yeah.
Could I ask a question about the previous?
Yeah.
Matlab code?
Yeah. Can I work this problem out and then answer the question? The reason I'm trying to solve this problem is because these problems will be super helpful when you work out your assignment 2. So I want you to have solution as you work through the problems. So, but I'll get to your question without fail. So first and foremost, 0 R1 cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. Next thing is x1, y1, z1, x0, y0, z0. Can you see x1 is aligned with x0, y1 is aligned with y0, z1 is aligned with z0. So 0 R1, cosine theta 1, sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. Now I need to write down the homogeneous transformation matrix 0 H1, cosine theta 1, sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1, 0, 0, 0, 1. And then what I need to do is I need to fill in the blanks here, here, and here. This is the distance between the frame 0 and frame 1. And as you can see that this distance is 0, this is around x0. This distance is 0. And if you look at the distance along z0, which is a1. Next thing, please note the second joint is a prismatic joint, which means 1R2 is going to be identity. And I'm going to write here x2, y2, z2, x1, y1, z1. Please see x2 is aligned with y1. x2 is aligned with y1. y2 is aligned with z1. And z2 is aligned with x1. So now what I need to do is I need to carry out this multiplication. First row, first column. So first row, first column gives me 0. First row, second column gives me 0. First row, third column gives me 1. Second row, first column. And you may ask me, why am I doing this? Because if I pre-multiply or post-multiply any matrix by an identity matrix, I get the same thing. Can you see that this is an identity matrix?
Yes.
So if I multiply, pre-multiply or post-multiply, the answer is not going to change. So essentially, this is going to become 0, 1, 0. Now, with this, I need to write down the homogeneous transformation matrix. And homogeneous transformation matrix would look like 0, 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1. The key question is, what is here, what is here, what is here? This is around x1, this is around y1, this is around z1.
Can we do the same strategy that we did last time and put 0 there for now and then do a translation for the next frame, or do a translation?
We don't have to do the translation here because all the frames follow the rules.
So Z1,
Mhm.
X. Aha. Okay, frame part. Roger that. Good job.
So x1, as you can see, this distance is 0. y1, this distance is 0. This distance is d2. And the last frame, again, so it's 2R3. It's a prismatic joint. So it's going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. X3, Y3, Z3, X2, Y2, Z2. So X2 is aligned with X3, Y2 is aligned with Y3, and Z3 aligned with Z2. So this is going to become identity matrix. Identity multiplied by identity is going to give you identity. Now the homogeneous transformation. 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. And here, here, here. Now let's go back to the kinematic diagram. And as you can see, the distance between the frame 3 and frame 2 is D3, and that is along Z2. This is D3, 0, 0. So 0H3 is 0H1, 1H2, 2H3. And this can be done in MATLAB. Are you with me so far? Any, yeah.
I think A's and B's. Are we taking horizontal distances as A's and the vertical as B's?
No, you can take distances. Those are just conventions. So basically, if you look at the convention in robotics textbook, A's are the fixed distances, D are the changing distances. For example, prismatic joint, it can vary in length, right? So D2 can vary and D3 can vary, but A1 would remain fixed. That's how the convention is. Can you work this problem out in MATLAB?
Yeah.
Now, let me take one problem and then I want to solve one problem with the exception. So this is a classic 3D. I don't know if you notice, 3D printer is a robot. It's a Cartesian robot. So it's a robot that can go in X, Y, and Z direction. So which means it has 3 prismatic joints. So I'm gonna show you a simple PPP robot. So you have this prismatic joint. There is another prismatic joint. And then there is another prismatic joint. I'm just going to show it over here. So this is the P. This is another P. There is one more P. So 3 prismatic joints. Are we allowed to change the orientation of the joint? Homework, like stretching the joint. I don't know what you mean by stretching the joint. As long as the kinematic configuration of the robot is retained, you don't convert a prismatic joint into a rotary joint, I think you should be okay. So first and foremost, add the coordinate frame Z0, Z1, Z2, and here is the end effector, and then complete the triad. X0, Y0. I will complete this triad. Y1, X1, X2, and then this becomes, to draw this correctly. This becomes Y2, and I'm going to duplicate this coordinate frame. X3, C3, Y3. So the good news here is there are no rotation matrices. There are just prismatic joints. Yeah.
Shouldn't the Z of the third joint be like shifted?
Which shifted?
Sorry,
Because it's parallel. with
Yeah, yeah.
Z- Yeah, so Z3 and
Z3
Z4 are
should
parallel.
be, yeah, Z3 and X2 should, sorry, Z2 and X2 should be switched, I suppose, because it's moving in the third dimension as well.
Okay. Before I answer that question, let me check. So Z0, Z1, Z2, they are correct. X1 is perpendicular to Z1, Z2. That first frame, X2 is perpendicular to Z2 and X2 is perpendicular to Z1.
Shouldn't Z2 be like in the perpendicular, like the Z direction?
Didn't I? Let me draw this properly.
Yeah, yeah. The third prismatic joint is redundant. It should be perpendicular to.
Yeah. Correct. That is absolutely correct. That okay. No question with the frames, right?
No, not the frame selection, but.
Okay. The question is the robot. Robot is redundant. That is correct. So basically, if I add the third joint in the vertical direction, you get X, Y, and Z.
Yeah.
But if I were to do that, that will give you the solution of the problem.
But then that's a 3D printer, right?
Yeah. But I want you to solve 3D printer because that is one of the assignment problems.
Okay.
Okay. So, but you are absolutely right. Rather than adding the joint articulation in the horizontal direction, if I add the joint articulation in the vertical direction, you get articulation in X, Y, and Z. This is not in X, Y, and Z, but you can follow the same rules, and answer is going to be pretty much similar. So 0 R1, 1 0 0, 0 1 0, 0 0 1. Then you have X1, Y1, Z1, X0, Y0, Z0. X1 is aligned with Y0. Y1 is aligned with Z0. And Z1 is aligned with X0. You agree with me? This is an identity matrix. So the solution here is 1, so 0, 0, 1, 0, 0, 0, 1, 1, 0, 0. So now I need to construct the homogeneous transformation matrix 0H1, 0, 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1. And now please note, I'm going to give you some distances. This distance, I'm going to call D1, and that distance is along Z0, 0, 0, D1. Now I need to proceed further. So 1 R2. Again, it's an identity matrix. But you need to add projection matrix x2, y2, z2, x1, y1, z1. So x2 is aligned with x1, z2 is aligned with y1, and y2 y2 is y2 is aligned with minus z1. y2 is aligned with minus z1. So when you multiply, you are gonna get this matrix, and this is gonna become 1. We'll just go 1h2. 1h2 is gonna look like 1 0 0 0 0 0 1 0 0 minus 1 0 d2 0 0 0 1. Then last but not least, I will write the rotation matrix here. That again is going to be identity 2 R3. No, you cannot skip the rotation matrix because you will have projection matrix. Even though the rotation matrix is going to be identity, your projection matrix is going to change that identity matrix. So please do not skip the rotation matrices. Even though it's a prismatic joint, write the rotation matrices at identity, because those matrices will get changed depending upon the projection. If you can directly write down the projection matrices just by looking at it, that's fine. But as long as, at least for first few problems, I would recommend write the rotation matrices. 1 0 0 0 1 0 0 0 1. So x3, y3, z3, x1, x2, x2, y2, z2, x3 is aligned with x2, y3 is aligned with y2, and z3 is aligned with z2. So everything is identity. So what that means is I can just write 3h3 1 0 0 0 1 0 0 0 1 0 0 0 1. And now if you look at the distances, this is d1, d2, and I'm gonna give you the last distance, d3, and that is along z2. So 0 0 d3. Now what you will do is 0h3 is equal to 1 0h1 multiplied by 1h2 2h3, and you can do this in MATLAB. There is last problem that is actually super important problem, wherein you again have the violation of the rules. I don't think I have enough time to solve that problem, but I will work that problem out in next class. So you had a question about the MATLAB script, right? Yeah. Any questions from my online students?
Sir, hello.
Okay, so I'm gonna switch. Okay, picking up parts. Tuesdays, and actually Borna will send out an email to everyone saying when to pick up the parts. I'll ask him to send an email. So if you perform the silence, please. If you perform the matrix multiplication in MATLAB, online students cannot hear me, so please be silent. Silent. So recommended infill for the printed parts. Depending upon your 3D printer, you can actually go to the dense 3D printer so that your robot will be rigid. Otherwise, you'll notice that if your robot is flimsy, then it will start vibrating. For your assignment, this is an important question. If you work out the problem in MATLAB, what you should do is you should upload the script and the MATLAB answers along with your work, handwritten work. So just don't copy the answer. Upload the MATLAB script and MATLAB answers. Okay. Question?
You want the .m file or like the public MATLAB file?
Anyone is fine.
Can we do all the questions in one file?
M files, you can just you can do $% sign and then you actually have that coded one, problem 1, problem 2, problem 3, problem 4. Okay. Any other questions? I'm going to show the MATLAB script real quick. Okay, tell me, did I make a mistake in the script?
No, sir, I don't think so. Basically, I wanted to get the position vector in the final matrix. Final percentage 0.3. So the cost has a two times theta there. If the theta is like suppose 45 degrees, why should we get the final position matrix as 0?
Okay, let me show you like this. So if it's theta 2, and let me think about it for a second. If theta 2 is 45 degrees, why did you get cosine theta 2 as 0? Let me think about this and I'll get back to you. But there is always possibility that I might have made some mistake in the pluses or minus signs here, and that would have messed up the answer.
I got that same answer.
So I would work this problem out again, and then I will get back to you. But I see what you're saying. But this big expression gets simplified. Anyway, I'm going to stop here, and I will definitely try to answer that question by next class. Yes, you're allowed to do that. We're on campus to find our recordings. I was looking at